to Lab 3, Black Holes and Orbits. So here's the table of contents. In part 1, the purpose is to simulate the orbit of a star around a black hole and use the data to generate an estimate of the mass of the black hole based on the gravitational force on the star. The formulas used were FNet parallel, FNet perpendicular, and universal gravitation. The result of the code was a visual representation of the orbit and accompanying forces, as well as the mass of the black hole. In part 2, the purpose was to simulate the movement of a spaceship and moon while taking into account the gravitational forces from the planet and the moon itself. The formulas used were the velocity and position update formulas and the formula for universal gravitation. The results showed how universal gravitation from various objects can affect a spaceship simultaneously. So here are the main ideas. We have Newton's second law, the momentum principle and velocity update formulas. We have the position update formula. I don't really have time to explain each individual thing. This is just a quick overview. So I also used the concept that FNet is the sum of its components. So I didn't have to find FPerp. I just subtracted F parallel from FNet to find FPerp. And then we have universal gravitation. Newton's law of universal gravitation states that every mass in the universe attracts every other mass with a force that depends on their masses and the distance between them. Okay, so for part 1 of the code, this is my initial conditions. The system is the star and the surroundings are the black hole. The lab gave the star's mass, and the black hole has the mass that we're finding. And then the others are just like constants. So this is finding FNet. I used the equation on the right, and the code kind of reflects the equation. To find FNet, I use the initial and final velocity vectors to find delta V, and then use that to find change in momentum, which I used to find FNet. And then this is FNet's components. So I have FNet parallel on the right, and then I also found that FNet previously, and then to find FPerp, I just subtracted F parallel from FNet. Okay, and then to find the mass of the black hole, you can see on the right, I showed how to get the mass of the black hole derived from the universal gravitation formula, and then my code just reflected that formula. Okay, here's the vector representation. So the orange vector is FNet, and it points toward the black hole for the entire orbit. The blue vector is FNet perp, and it points toward the center of the kissing circle. And then the pink vector is FNet parallel, and it changes based off of the magnitude of momentum. Okay, and then this is just the output of the code. I did add a line that found the average mass of the black hole. So you can see that in the bottom line there. Okay, now for part 2. So these are the initial conditions which were already given, and then the system and surroundings did change based off of what was being calculated. So for example, when the spaceship was the system, the planet and moon were the surroundings, and then they all changed based off of what we were finding. Okay, this is finding FNet on the moon. So I found FGrav on the moon by the planet, and then on the moon by the spaceship, and then found total by adding those two together. And then this is literally the same thing from the previous slide, except we're finding FGrav on the spaceship by the planet, and then FGrav on the spaceship by the moon. Okay, so now to make the move, we have to update the velocity and position of the moon and spaceship each time it passes through the calculation loop. So the formulas on the right kind of show what I did for that. Okay, I have to hurry. This is the output of the code. You can see the pink is the spaceship and the blue is the moon. Okay, so some possible errors. Since the lab is computational, there are less opportunities for errors. So that didn't make a big difference. There are no similarities or differences. So what does it mean? The net force is what makes something speed up, slow down, or change direction. The rate of change of momentum tells us how quickly that change in motion happens. Okay, And then the gravitational forces between the planet, star, moon, and black hole should be included, but the black hole's influence would likely dominate the interactions, especially since it is very massive. The star-planet and planet-moon interactions would still be important, but comparatively less significant. Alright, that is everything. Thanks for watching.